In graph theory chapter, I already discussed graph terminology and special type of graph. In this topic, I discussed type of graph like simple graph, complete graph, cycle graph, wheel graph, bipartite graph, complete bipartite graph, matching. Next topic is representation of graph and graph isomorphism. There I discussed how can I represent graph rather than graphical representation like adjacency list and adjacency matrix representation. And in graph isomorphism, how can check two graphs are equal or not. Next topic is connectivity. In connectivity, first I will discuss what is path. Path is a sequence of edges by which we can travel from one vertex to another vertex. So you can say a path is a sequence of edges that begin at a vertex of a graph and travel from vertex to vertex along edges of the graph. Suppose this is one vertex V1, V2, V3, V4. These are some vertex and there are some edges. So you can say V1 to V4 there is a path and that go through these edges E1, E2, E3. As the path travels along its edges, it visited the vertices along this path. So that is the end point of these edges. Like for E1, endpoint are V1, V2. For E2, endpoint are V2, V3. For E3, endpoints are V3, V4. So there is a path from V1 to V4 that go through E1, E2, E3. Now definition 1, it's about path. Let n be a non-negative integer, means n is a positive integer and G is a undirected graph. A path of length n from U to V. U is the start vertex, V is the end vertex. In G is a sequence of n edges E1 till En of G for which there exists a sequence x0 equals to U, then x1 till xn minus 1 and xn equals to V. So there is a vertex U, V and there are sequence of edges like E1, E2 till En, and suppose this is x0, this is x1, this is x2 and this is xn and previous is xn minus 1. So here u equals to x0 and v equals to xn. A vertices such that ei has for I equals to 1 to n. So the edge sequence starting from 1 till n. So e1 till en. The endpoints xi minus 1 and xi. When the graph is simple, we denote this path by a vertex sequence x0 till xn. So we can simple write the vertex sequence to represent a graph. The path is a circuit if it begin and end with the same vertex. If start vertex is same as end vertex, then that's called as a circuit. Or we can say simply u equals to v. If u equals to v, then that is a circuit and has a length greater than 0. Means there are some more vertices between u and v. The path or circuit is said to pass through the vertices x1, x2 till xn minus 1 or traverse the edges e1, e2 till en. A path or circuit is simple if it doesn't contain same edges more than once. Means there is no repetition of edges, then that is a simple path or simple circuit. We can say a path passes through vertices and traverses through the edges. So in simple way, you can say a path is a sequence of edges from u to v by which we traverse from u to v. In some book, rather than path, they use walk. So walk and path both are same. The term walk used instead of path. Closed walk means it's a circuit. When start vertex is same as end vertex, it's called as a closed walk. And the trail is denote for walk that has no repeated edge. Means for simple path, we use the term trail. So path and walk are same. Circuit and closed walk are same. Simple path and trail are same. When we are using these terms like walk, closed walk, trail, then path is used for trail having no repeated edges. Now example 1, in a simple graph shown in the figure, ADCFE is a simple path. ADCFE is a simple path having length 4. There are 4 edges included in this path. We are traversing from A to E because AD, DC, CF and FE are the edges for this path. Now DECA, E to C, there are no edges. So that's why DECA is not a path. So for path vertex sequence, there should be edges in that sequence, right? Next, B, C, F, E, B. It is a circuit having length 4. Now the path A, B, then B, E, then E, D, D, A, B. It's not simple as AB is repeated twice. Here is AB, here is AB. So this is not a simple path as one edge is repeated twice. We discussed path for undirected graph. Now path for directed graph. Definition 2, let n be a non-negative integer and G is a directed graph. A path of length n from U to V in G is a sequence of edges E1, E2 till En of G such that E1 is associated with x0, x1, E2 is associated with x1, x2 and so on, where En is associated with xn minus 1 and xn. Here x0 equals to u and xn equals to v. It's same as previous. When there are no multiple edges in the directed graph, the path is denoted by the vertex sequence x0 till xn. So we can represent the path by a vertex sequence when there are no multiple edges. A path of length greater than 0 that begin and end with same vertex called as circuit or cycle. Previously also same, that was for undirected, here is for directed. A path or circuit is called simple if it doesn't contain multiple edges. Means same edge is not repeated more than once, then it's called as simple path or simple circuit. In simple way, you can say there is a directed path from U to V if there are directed edges from U to V. Next, definition 3, it's about connected and disconnected graph. An undirected graph is called connected if there is a path between every pair of vertices, and it is called disconnected if there is no path between every pair of vertices. Or in simple way, you can say if a graph is not connected, called as disconnected. Also, you can disconnect a graph by removing some vertices or edges or both to produce a disconnect subgraph. Now example 2, we have two graphs G1, G2. G1 is connected whereas G2 is disconnected. There are two connected component, or we can say two connected subgraph. The graph G2 is not connected, so there is no path between A to D. Even there are no path from C to D, C to E, so we can say this is disconnected. Next, theorem 1, there is a simple path between every pair of distinct vertices of a connected undirected graph. This is a connected undirected graph, so you can find simple path between every pair of vertices. Simple path means the edges are not repeated. Next, connected component. A connected component of a graph is the maximal connected subgraph of G. Like in G2, A, B, C is a connected component, D, E, F is a connected component. A graph G that is not connected has two or more connected components that are disjoint and have G of their union. So here this ABC and DEF union is G2. So there are two connected components whose union is a graph. Next, example 3, photo the connected component of the graph H shown in the figure. This is H. There are three connected components. One is A, B, C, then D, E, then H, G, F. So there are three connected components for H, or we can say three subgraph H1, H2 and H3. H is the union of three disjoint connected subgraph H1, H2, H3, and these subgraphs are connected component of H. So H is the union of these three subgraphs. Sometimes we can remove a vertex and that will make the graph disconnected. So that vertex is called as caught vertex or articulation point. In next lecture, I will discuss more about caught vertex and caught edges. In today's lecture, I discussed path for undirected graph and directed graph, circuits, If start vertex and end vertex are same, then it's a circuit. Simple path or simple circuit. If no edges are repeated, it's called as simple path or simple circuit. Connected graph and disconnected graph. If there is a path between every pair of vertices, it's called as connected. If a graph is not connected, it's called as disconnected. So a disconnected graph is a union of connected component, or you can say maximum connected subgraph are called as connected component. In next lecture, I will discuss cut vertex and cut edges. If today's lecture is helpful for you, please like, share and subscribe. Thank you.